Greetings, student. This is a recording of one of Garnett's online math lesson classes. You have been granted access to watch this video because you're a paying student and I have seen it fit to provide this recording to you. However, it is important that you know you're not allowed to share this video with persons outside the lessons. This policy is so that my services are kept only to my students. Thank you, and I do hope you enjoy and learn from this video.
The last class we began to look at the properties of a circle, and we also started looking at the calculating certain aspects like the sector and the segment, particularly those two, right? Now we worked our first example. We found the area of the sector. Again, area of sector is just finding a portion of your total area of the circle, right? That's what the formula is. So we found the area of a sector, and then we went forward to the second question, which says to find the area of the triangle, right? This is something that I don't want you guys to forget. All these triangles that are in the sector are usually isosceles triangles because there are two radii. The two lines coming from the center are two radii, so they would have the same length. Don't forget that. Usually students sometimes forget that when we move on, even when we move on to other stuff, once you see two radii making a triangle, right, with a chord, or yeah, most likely it'll be a chord. With a chord, isosceles triangle come to mind right away, right? Remember that, don't forget that fact. Even when we move on to other aspects of the circle, like circle theorem and so on, don't forget that. It will show up back, right? So we identified that there's an isosceles triangle, and we also were introduced to previous classes, we're introduced to three ways in calculating area. The only two ways that are applicable here are Heron's formula and the length of two sides and the angle between them, right? So Heron's formula is the square root of some products and differences, and with S being the half the parameter. Now, fast forward, we calculated the area of the triangle, triangle POQ, using both methods, right? Both the area, both Heron's formula and the angle with the two sides, right? Now this is another way of finding it, and this one is really because this is an isosceles triangle, right? I'm going to explain this, but something tells me none of you guys might remember it, but I'm going to explain this. This is a neat trick. Not a lot of people know this, but this is a neat trick that you can do, and you can, that more or less makes it so you can actually use the other formula, half base times height, right? What I want you guys to focus on is what the notes that are in blue. You see what's highlighted in blue? That's what I want you guys to take away from it. Don't get confused with the calculations and so on. Once you remember this is what I want you to take away, right? So it's gonna get a bit confusing. So I'll explain this and then we move on with the other questions. Now with isosceles triangle, because their geometry is so, let's say it's a perfect, the isosceles triangle you could view the isosceles triangle as it's symmetrical, right? Not all triangles are symmetrical. Equilateral triangles and isosceles triangles are perfectly symmetrical. And because of that, I'm appealing to your visual learning. I'm appealing to visual learners right now, right? So going it over, we have an isosceles triangle, meaning that two sides are equal, right? And we can notate that using our double dash or a dash, right? Or a slash, right? So what I'm telling you now, that a feature about these isosceles triangles as well as equilateral triangles where all the sides are equal, right, is that you can split them directly in half. And you notice that I'm splitting it in half here between the two equal sides and not like here. That wouldn't be symmetrical, right? It has to be between the two equal sides. So that take note of that. However, if it was an equilateral triangle where all the sides are equal, forgive these drawings. Good. So if it was an equilateral triangle where all the sides are equal, so let me put the
Sir,
the
still hearing
dashes.
it.
You're still hearing it. All right.
Are you breaking up?
Right, so I'm using the headphone microphone. You guys hear me?
Yeah.
Yeah, so as I was saying, the isosceles triangle and the equilateral triangle are symmetrical, right? And because of that, this is the equilateral triangle, and we can split it in half, right? We can split it perfectly in half, right? And you use, for the isosceles triangle, you need to use the two lines. You need to split it between the two equal length, right? The two equal sides. Now with the equilateral triangle, it doesn't matter where you split it because all the sides are equal, right? So you would be splitting it between two equal lines no matter where you cut. So when we split the isosceles triangle into two equal halves, we create two right angle triangles, you can see. So we're basically cutting it directly in half. And like with the circle, if we split a circle in half, we get two semicircles. Think of this as two semi-triangles. There's no such thing as a semi-triangle, but this is a triangle, right? They would be 90-degree, right? It would be two right angle triangles because this line that cuts will be perpendicular to the base, right? So we would have created two right angle triangles. So we have two right angle triangles. Now, another thing that I want you guys to recognize is the fact that we can use the original lengths of these lines to get the measurements for our two new triangles. So let's use the same stuff that are here. The angle, the vertex angle of the original isosceles triangle is 45 degrees, right? We're splitting the triangle in half, meaning that we're splitting the angle. We'll be splitting the angle. If you notice, we're cutting this angle, right? We'll be cutting this angle in half. So half of 45 is 22.5. So the angle over here is 22.5 and 22.5, right? That's the angle, right? Now, we're also splitting the line, the base of the triangle, right? This line, we're also splitting this line in half, perfect half. So this line in this case was, the entire line was, all right, I'm writing all over this. Let me use a different color. Yeah, the entire line was 2.7 centimeters, right? This was 3.5. Over here was also 3.5 because it's an isosceles, right? Good. So we're splitting the angle in half, so it only makes sense that the two new semi-triangles, there's no such thing as a semi-triangle, I'm just saying that. So the two new half triangles, the angle at the top, the vertex would be 22.5 degrees. Now we're also splitting the 2.7 centimeter line, this base, in half. So it only makes sense that the length here would also be half of this line because it's, again, perfect sphere, perfect, splitting it perfectly symmetrical, two halves, right? And that is
Sir.
1.35. Yes?
You're breaking up.
I'm still breaking up. I know you. Am I still breaking up? There might be a connection issue,
right? That might be a connection issue. If there's the case, I don't know how I could help you with that. Right? Good. So that is how we end up with that. That's what I'm trying to showcase here, right? And that's what I'm telling you in these notes, is that once you have the same thing applies with the equilateral triangle, right? You're splitting it in half. The angle at the top here will be split into two angles. That will be your two angles at the top there, and the line, the baseline here, would also be split in half, right? Now, of course, the original side was 3.5, and over here was 3.5. So that will come back 3.5 and 3.5. Right, so it's still 3.5 on the where we didn't cut, right? The symmetrical line, the line of symmetry, right? We didn't touch our equal sides. So this just telling you, split a isosceles triangle in half, get 90 degrees, cut the vertex angle, divide that by 2, and the base, the line that you're cutting, in half, and you'll get the bases for the two triangles. That's all these are telling you, right? These notes here. Good. So I want to move on to, and I changed this because I know the color in here. I changed the color there. Right? So we found the area of the triangle. Now we're moving on, right? So we found the area of the triangle, right? Using Heron's formula and the or using the length of two sides and the angle between them, right? So, and we also calculated the area of the sector. So the segment is easy to find because once we have the area of that sector and we take away the area of the triangle, what is left is the segment, right? Hence why the area of the segment is equal to sector subtracted by the triangle, right? So we just use the what we found so far, the area of the sector subtracted by the area of the triangle, and we ended up with our 0.41 centimeters squared, right? Which is the area of the segment, right? We went through this last class. So here's where we left off, where was to calculate the length of the minor arc. And I was saying before we closed off that the arc is a portion of the circumference, right? So to find the length of the arc, you're basically just finding the circumference, which is the perimeter of the circle, and then finding a portion of that. So you're finding a portion of the perimeter of the circle, or the circumference of the circle, right? So, and that's what's in the formula. So 2 pi r, that's the perimeter or the circumference of the circle, multiplied by theta divided by 360. Now, they want us to find the length of the minor arc. You notice they will ask ambiguous questions like these because they expect you to know what the minor arc is, right? Before I explain to you, there's a minor and major segment. When we cut, when we use the chord and we cut, we have a minor and major segment, right? We have a minor and major sector. Now I am identifying that for you. The questions, in the questions, you got to be able to identify what's the major segment and what's the major, the minor segment and that kind of thing. Because I could have asked you to find the area of the, no, yeah, I could, right? I could have asked you to find the area of the major segment. That's a complication. Yeah, I wouldn't do that, right? So, but I could ask you to find the area of the major sector. Not because you see 45 degrees here and these numbers here. You know that this is the minor sector, right? Meaning that we have the two radii slicing it like a pizza. This is the minor sector. The major sector would be this area, right? And we'll look at it. I will look at a question where you got to look at the major sector because there are some extra steps that we need to, some extra things that we need to look at, especially the angle, right? So minor, be able to identify what's the minor segment, the major segment, the minor and major arcs, and the minor and major sectors, right? Small and big, this is all it means. The smaller one and the bigger one, that's all minor and major means, right? So that should be simple enough. So we're looking at the minor arc, and we know that the arc is just a portion of the circumference, right? So PQ is a portion of, PQ is a chord, or you can look at PQ as this curved line going around here. And this would be a minor arc. Yeah, no problem. Yeah, so this would be a minor arc, PQ. Now the major arc, of course, would be the rest of the circumference, which is, you can look at that, this is PQ, but the major arc, right? So this is the major arc, the rest of the circumference. So from here all the way around here, my major. So what we want to find is this minor arc, right? And that's what the question is asking here for. Minor arc, they're referring to this portion, right? Minor arc PQ. So PQ, you look at the card, right? And take that as a reference, right? P and Q, and look for the minor arc, the smaller one, the smaller line. So the formula is always the same, no matter whether you're looking at the major or minor arc. We know the formula remains the same, right? So the length of an arc is L is equal to 2 pi r theta divided by 360. I've forever been telling you theta refers to an angle. Theta always refers to an angle, right? And theta, right, refers to the angle. What angle, you might ask? Well, there's only one angle on the screen, right? So obviously it's that angle. No, I don't want you to think like that, right? So, because I'm gonna trick you if this is where you think it. All right, so what angle? Yikes, where did you go? Okay. So what angle? Yes, it's the 45-degree angle. So yes, in this situation, you are correct. That's the only angle on the screen. So obviously that is it. However, what I want you to pay attention to is that this angle, how you know that this 45 degrees is the angle of the arc, how you know it's the angle of the sector, how you know it's the angle of the segment. Well, segments don't have angle. So this is how you know it's the angle of the sector, and this is how you know it's the angle of the arc. And we will do a quick exercise just now where we go through a bit of identifying the angle of the segment of an arc and the sector, because that causes some confusion. So it is 45 degrees. The angle for this arc is 45 degrees. So theta is equal to 45 degrees. Not gonna fight you down there. But the reason why theta is equal to 45 degrees is because the angle, now PQ, right? The angle between P to the center of the circle and OQ to the center of the circle and Q to the center of the circle, the angle between the two lines, P and Q going to the center of the circle, is 45 degrees. And what's even more important is the fact that the angle is facing an arc, right? This angle is facing that arc, right? It's in front of it, it's facing it. However you want to look at it, this angle, 45 degrees, is facing that arc. So 45 degrees is that angle, right? So theta is equal to 45 degrees. So we can just substitute. We know the radius, right? The radius of a circle doesn't change. It's always the 3.5 from earlier, right? So 2 pi r, 2, we're using pi as, like before, we're using pi as 3.14, and r, 3.5 centimeters, right? Multiplied by our theta, which is the angle of the arc, the angle for that arc, divided by 360 degrees. Yeah, divided by 360 degrees, right? We know this 45 over 360 is 1/8. Simple maths, and we get an answer. We can do so. All right. You guys don't have any questions to me, so I'll ask you guys questions. If nobody asks any questions, I can ask other questions. That's how you claim you're seeing these two sectors, right? You're seeing this?
Yeah.
Good. So I have one of them shaded in green and one of them unshaded, right? This is your target. You have two sectors, and one is a major sector and one is a minor sector, right? The question I want to ask is, of course, you know, the one in green is the minor sector. I should have asked that, but the one in green is a minor sector, obviously, because it's a smaller piece, is a smaller slice than
the one, the unshaded portion. Right, so everything else here is a major sector, and here is the minor sector. So we can identify the sectors. Now, let me put an angle here. All right, this is the angle that I'm putting. Then I'm gonna call it 270 degrees. Yikes, let me use a different color. And then what I want to know is me fault. Yeah, it's 270 degrees. This angle here is 270 degrees. Okay. This is 270 degrees. So y'all already know the angle of the major sector. So the angle of the major sector is I should just put those out. The angle of the major sector is indeed 270 degrees. But just so I'm asking you the angle of the minor sector. Right, so 360 degrees minus 270 degrees will give us our 90 degrees, which is correct. Does the angle of the minor sector, right? This is 90 degrees. Why you subtract 360 from 270 is because a full rotation or a full circle is 360 degrees, right? So if you want to know the angle of the remaining portion, if this angle here is 270 and you want to know the angle of the remaining angle over here, you just need to subtract this angle from 360 and that will give you the angle over here. So coming down to the second one, the angle up here is 120 degrees. So you can already guess what you need to do to get the angle at the bottom here. What's the answer? What's the answer? Somebody tell me.
240.
240. It's a 240. Right, so the angle is 240. Right, so the angle of the major sector is 240. So I'm writing an angle. Yeah, so 240 degrees is the angle of the major sector. And the angle of the minor sector is 120, right? The angle within our minor sector over here is 120. The angle of the major sector over here is 240 degrees. The reason why I'm emphasizing this and chose to even go about asking you guys this is because you won't always get the angle. I could ask you to find the angle of the minor sector and give you the angle of the major sector. You got to be able to say, well, yeah, I got a minus it from 360 to get the angle of the minor sector. Because remember, you got to get theta, and theta is the angle. If depending on if what I ask, usually it's the minor sector they usually ask for, right? So you got to be able to see that and this is why I said theta is not always the angle that you see in the circle. It's not because you see 220 that case 120 degrees, you see 120 degrees, and I'm asking for the area of the major sector, you're going to use 120 as theta. Be very careful to ensure that you're using the angle of that sector and not just the angle that's in the circle, right at the center there, not just the angle. It needs to be the angle for that sector. I'm asking you to calculate the length of PQ minor arc. These two are radius, right? These two are radii. But so I'm asking you to calculate the length of the minor arc, right? And we know the area, the length of an arc. I'm writing E. So we know the length of an arc is. What I want to find is, like I can't spell. Find. Yeah. So what I want to find is the minor arc. PQ, right? The length, right? L. I want to find L for the minor arc PQ. And we know L is equal to 2 pi r or pi d theta divided by 360 degrees. Now we don't have r, we'll just leave r as it is. But what I want to know is what is the angle for the minor arc? What angle would you use? What is the value for theta? What would theta be equal to? That's what I want to know. What is going on? Yeah, but what I want to know is theta. What is the value of theta, given that I want to find the length of the minor arc PQ, right? So we're not looking at the sectors, we're looking at the arcs. Same concept applies. So anybody could shut up here. So
Sir, 90.
say 90, right? 90 degrees, because the angle of the angle, this is an angle, but this is the angle of the minor arc, because this arc is for the major arc, which is on this side, right? Which is this arc. So but I'm not finding the length of this arc, right? If I use this angle, this will give me the length of the major arc, right? So because I'm finding the angle of the minor arc, I have to go and find this angle, right? The length of the minor arc, sorry. I have to go and find this angle, which just same thing as like before. Subtract it from 360 and you will get this angle. So ensure you're using the correct value for theta by looking at which one is the angle of the minor or major sector or the minor or major arc, right? Make sure that you look at it, you're using the correct value for theta. Here you have the question: O is the center of the circle, OQ is 3.5 centimeters, but right? OQ is 3.5 centimeters, and the chord PQ is the chord, is 6.1 centimeters. Calculate the area of the sector, the minor sector, POQ. Calculate the area of the triangle POQ, and then you're going to calculate the area of the shaded segment. Then you're going to calculate the length of the arc PQ, right? Particularly, I would ask you guys to calculate the both arcs, right? Length of both arcs. You should be able to do that. But I'm going to specify one. You should, right? I'm going to specify one. Right, we're going to look at most cases, it's usually the minor arc. I can tell you that if they don't specify the arc, it's usually the minor one, right? You should, but I don't think everyone specifies which arc. But it's usually the minor arc, right? Most of the stuff here is minor, minus the shaded area. The shaded segment is usually the minor segment, usually the minor sector. So usually you're looking at the minor part of the circle, right? So so you're looking at the minor arc. So calculate the length of the minor arc. I'm going to give you guys about, I think from now, let's write down the variables for whenever you're using a formula. One neat trick, especially the science students usually use, is they write down the variables, the value for each variable before they plug it into the formula. Right, so for the first one, we're looking at the area of the minor sector, POQ. And if you then recognize this already, the minor sector is this portion, right? This is the minor sector. This is, I'm shading it gray, right? This is the minor sector, right? Again, look for those two radii slicing a pizza, slicing the circle like a pizza, right? So the two radii are there, and we have our, so we want to know the area of the minor sector, right? I don't like writing. Right, so we know area of minor sector is equal to area of any sector actually is equal to not 2 pi r square, sorry. All right, a pi r square theta divided by 360. Before you go ahead and start plugging in, what is the radius? What is the length of the radius? So what is r? Shelia, what is r?
3.5.
3.5, right? The radius is 3.5, right? They didn't specify radius is 3.5. They give you OQ, and you would have seen that OQ, looking at the diagram, OQ is the radius. So the radius is 3.5 centimeters, and the theta, which is the angle, we're looking at the minor sector, so angle of the minor sector would be equal to what, Josiah? What is the angle? What is theta? What is the angle?
120 degrees.
120 degrees. Yeah, 120 degrees, right? So we have R, we have theta, we can find the area just by a plug and chug, right? So I didn't specify pi, no one asked either, but I didn't specify pi, so free rein there, but usually I would have to. Usually you indicate what pi is, right? The question usually indicate what you should use as pi, either 22/7 or 3.14, right? I forgot to do that, but let's use pi as 3.14. If you notice, I've been using pi as 3.14 throughout this exercise, right? So 3.14. If you use 22/7, no problem. Yeah, so it's going to be a bit different, but no problem. I didn't specify, so I'm not going to penalize anybody. Meters around that. Again, I know I didn't specify value, so you might be a bit different from that, right? But around 12 point, around 12 is fine, right? So the next question is asking for the area of the triangle. No. Right, so the next question is actually area of the triangle, right? Area of triangle. All right, Rihanna, back to you. Actually, let me move that at 6:30. Yeah, one formula you could use is AB sine C, right? It's the simplest, the easiest one, the fastest, the one to give you the answer the fastest. So AB sine C, right? C being the angle, the length, and AB being the two sides and the length, and C being the angle between them, right? So A, we have two sides, we have 3.5, and of course, remember these triangles, once with the radii are usually isosceles triangles, so both sides will be 3.5 centimeters. So 3.5 and 3.5, right? Yes, Kazako.
I have a question. Isn't that formula half AB sine C instead of AB sine C?
Yeah. I forgot that. Sorry about that. It's half AB sine C. Good. Good spot. I'm thinking about the parallelogram, right? And then you divide this by 2. Multiply it, half it, whatever. So yes, Kazako, I haven't called your name either. Yeah, so what's the answer? I think I called everybody today. All right, Chilio already thought.
7.5 there.
7.5 centimeters. And last one. I'm out of time because I could double check your values that you use. Probably something went wrong somewhere, but that's gonna be it. Yeah, man.